So let's continue with this idea of compressibility and what it does to an aquifer. So I've just rewritten the equation that we came up with, that we defined for compressibility, which is the change in the thickness of the aquifer divided by its initial thickness, and both of those divided by the change in the effective stress. So we're going to define something called specific storage. And we denote that as S sub S. And our specific storage is going to be the term that we use to figure out how much water is coming in and out of an aquifer under confined conditions when the head goes up and down. So we define that specific storage as gamma times the compressibility plus the porosity times beta, which is the compressibility of water. So gamma is the specific weight of water. You already know alpha is compressibility, N is the porosity. And then beta is the compressibility of water. And as I wrote before, that's 4.4 times 10 to the minus 10th meters squared per Newton. Okay, so let's ignore this term over here for the time being. So that's the compressibility of water. We figured out that water is very incompressible, so it's really not going to factor in unless we're talking about rock. So let's assume we're working with an alluvial aquifer, and then we have this relationship, the specific storage is equal to the specific weight of water times the compressibility. Okay, and then we have for the compressibility, we can substitute in this relationship that we came up with before. So the change in aquifer thickness divided by the initial aquifer thickness divided by the change in the effective stress is equal to the specific storage. And we already figured out before that we could substitute in a value for or expression for head in for the effective stress by using a balance on that horizontal plane. And so we end up with negative of the specific weight of water times the change in head, and the specific weights cancel. So now we can write an expression for the specific storage, which is the change in the aquifer thickness divided by the initial aquifer thickness times the change in head. And we still have our negative sign out here in front. So what we're ultimately after here is we want to know how much water is going to come out of the aquifer when we change the head, because that's going to tell us what water is released from storage in an elastic sense when we pump an aquifer. That's what this expression for specific storage is good for. We can define another parameter, which is rather unimaginatively named storativity, which is the capital S, which is the specific storage times the thickness of the aquifer. Okay, so it's like the difference between transmissivity and hydraulic conductivity. Now we have storativity and specific storage. So we haven't really done anything besides redefine something that's a little bit easier to look at. All right. So now that we have this, we can bring this B naught over the other side, and now we have storativity is equal to the change in the thickness of the aquifer divided by the change in head. So if we multiply both sides times area, and by that I mean the some area of the aquifer that we're working with, just like we had when we had our plane for the balance of forces, we picked some arbitrary area to work with. So I'm going to multiply both sides times the area, and I'm going to when I multiply the top the numerator on the right-hand side, we can see that the change in the thickness of the aquifer times the area is going to be the change in the volume of the aquifer. And that's divided by the head. And so if we take the storativity, multiply times the area, multiply times the change in head, what we find is that's going to be the change in the volume of the aquifer. And when we compress the volume of the aquifer, it's going to have to produce the same amount of water out of the pore space, and we'll say that's V sub W. So I'll write that again. The storativity times the area times the change in head is equal to a negative of the change in the volume of water. And so this is the volume of water released or stored due to change in head. And we're going to use this a little bit later on to make up some equations that are going to help us to understand water flow and storage in aquifers.